Okay, in our next challenge, we're going to end up adding unsigned binary numbers. So this time, regardless of the initial size of these values, which are the same values by the way, we'll be ignoring the sign extension and we'll be simply zero extending to the matching sizes. So in this case, just create more space for this exercise, right? So if we take this first example, what we should have is simply taking these values as unsigned numbers, and here we just zero extending. So we're just adding these two binary quantities, and of course this will be a 0 and 1 as a carryover right here. And again, 1 plus 0 plus 1 is another 0 and 1 carryover. And this is 1, and this is also 1. So this is a binary result, but we must convert this binary result to a decimal value. So what we can do is, again, we can practice with the calculator. I will clear my calculator, and I will keep it at the byte level and just copy this into the calculator, but making sure that I'm in binary mode, copy and paste. So this gives me a decimal value 12. So we can write the result is this, and 12 to be a decimal equivalent. I'll let you practice with the rest of these, but just remember to fill in every single challenge and save often so that you preserve your work, and when you're done with all of this, just submit. If you have any questions, you can post your questions on our discussion forum in e-learning, and be sure to subscribe to it, because you will know when somebody will be providing an answer to your question. In our next challenge, we have a negative 27. So let's just take negative 27 and take a look at its representation. So basically, we need to take negative 27, figure out what is the 2's complement value, and represent it as 8, 16, and 32 bits. So let's start with the byte and switch to a decimal input and simply enter clear it and enter negative 27. You can see that the binary value is this bit pattern. I'll just copy it and paste it. So the next step would be to sign extend this 2's complement to a 16-bit. So let's switch to a bit view, and hopefully we can cycle through different sizes right here. So switching to 64-bit, double word is a 32-bit, and here's the 16-bit is a word on Intel architecture. So let's just try to copy it from here and paste it into this field. So this already inserts some spaces quite nicely. And let's also extend to 32-bit size, which will be a double word right here. So this has to be a 32-bit size bit pattern right here. Again, just be careful that everything is copied properly and we are using the right sizes. And the next question is, what does minus 27 as a 2's complement illustrate with respect to properties of sign extension as they pertain to 2's complement representation? My answer would be that sign extension does not affect the actual value, right? So sign extension is done when the data type changes to a larger size. However, you can see that all of these three variations of bit patterns represent the same negative 27 in 2's complement format. So once again, the answer is the sign extension does not affect the value. The value remains the same as a result of sign extension. this next question basically is a practice applying masks, and we have binary inputs, and we need to apply the AND operations in all of these examples. So again, we just can use a scratch pad to apply these operations, and this time this is not an addition. The AND operation needs to be applied to individual bits at their respective position. So recall that AND yields 1 only when both inputs are set to 1. So here we have 1, and we have another 1, and here we have 3 of them. The rest, I assume, should be set to 0, and from this input I can copy to my answer, and once again you can insert a space for the sake of readability. So you can apply it like this. And when we have AND used twice, you know that the ending is commutative, just like an addition. So if these inputs are exactly the same, keep ending them should result in the same outcome. So just again, I'll let you practice these examples on your own. Fill in the following truth table for a 1-bit OR operation. So here we need to copy and paste this entire truth table, paste this in, and replace question marks with our answers. So OR, of course, results in 0 only when both inputs are zeros, otherwise it's all set to 1. Remember to save your answers periodically. The ORing is very simple, similar to ending, so we can again try to apply this in our example right here. So this is an OR operation. I'm using my scratch pad again. So remember, so let's just say that whenever a 1 is present in one of the inputs, it's a 1. So only when when both are set to 0, we yield 0. So this is a mask, an OR mask. So this would be our mask in typical computation, and this would be our input. So this is where the ORing normally is taking place, and this is the result of applying an OR mask to this specific input and using this type of bit pattern as a mask. So I'm assuming that this would be my answer to this specific challenge. And now we have a mix of operations using NOT and OR and so forth. So just watch out for parentheses. We say that anything that's being placed inside the parentheses, of course, is taking higher priority, and we need to compute it first. So let's try a case like this and try to use this as a demonstration. So let's use this space right here and say that we need to perform these operations. So the innermost set of parentheses indicates this operation, so let's do it first. So once again, this is an OR operation, so quickly the result is 1, 1, 1, 0, and 1. So we can then replace the original input with the new input, but now get rid of the inner parentheses and replace this as this. Now we can try to figure out this AND, and so this AND should give us 1, 0, 0, 0, and we can finally copy and paste this one more time and replace the existing parentheses with this value. And now the challenge is to flip all bits So the answer is 0, 1, 1, 1. So this is the final answer to this challenge. And I'll just copy and paste it right here. So just to be careful by making sure that when you're trying to solve this with parentheses, all expressions in the innermost parentheses have to be given the highest priority, because it's like a grouping operation in a high-level programming language, and so therefore this has to be computed first, this has to be computed next, and finally we can apply the operation which is outside of any parentheses once we have decided what this is.